Hello. We are continuing to work through the art of computer programming. We are on section 1.1 in the middle of the exercises. And I don't quite know how today's going to go. We've gotten through the first 1, 2, 3, 4, 5 exercises so far. But they're going to get fairly mathematical soon. And let me just open Twitch so that I'm always paranoid that that my stream's not working. Great. Okay, looks to be working. Yeah, so we're going to be working through the rest of the exercises in this section, and then, we're going to see how those go, and then we're going to see how the start of the next chapter goes, and then we might shift to some more mathematics because my mathematics skills are not sufficient for getting through this book without having to do some other study. Part of the point of this project is to capture what it takes, I guess, what it takes to work through all of this. And so I will also be working through the mathematical study that I have to do on stream as well. I don't know exactly how much of that. Thank you, Spaceberry. I hope I do have an artful day. Yeah, we will see how that goes. Now, first thing I should say, if you are interested in following along with this in any way, I would suggest considering buying the books. They are not exactly cheap, but they're definitely worth it. Donald Knuth has committed a fair chunk of his, well, you may say it's the project of his life, so worth buying them. They come in a little box set now. I haven't got the box set because I'm waiting for the full set, but these books are all paid for, the PDFs. Just because they're PDFs doesn't mean they're totally ripped from the internet. Of course, if you are not in a place to afford that, then feel, of course, no pressure from me. But I thought I should say that since I am streaming them. Okay, so where we were last time, we'd gotten through this exercise. The highlighting here is terrible. We got through this exercise, showed that the procedure for reading this set of books that appears after the preface, etc., etc., etc. And now we're moving on to 6. I think after that they get fairly mathematical. Of course, this one's mathematical too. What is T5? The average number of times step E1 is performed when n equals 5. So I think that this is referenced earlier in the text somewhere, but I've forgotten where exactly it is. So this is about computing it. Yeah, I think there's some... Yeah, okay, here we go. Yeah, we're often faced with several algorithms for the same problem, and we must decide which is best. This leads us to the extremely interesting and all-important field of algorithmic analysis. Given an algorithm, we want to determine its performance characteristics. For example, let's consider the algorithm from this point of view. Suppose we ask the question, assuming that the value of n is known, but m is allowed to range over all positive integers, what is the average number of times Tn that step E1 of algorithm E will be performed? So this is basically the same as our question. In the first place, we need to check that the question does have a meaningful answer, since we are trying to take an average over an infinitely many choices for m. But it is evident that after the first execution of step E1, only the remainder of m after division by n is relevant. And this is because hello, Lexi T. That's not why, it's because discovered your videos a year ago, and I'm reading the Nystrom book of crafting interpreters. Cool. How's it going? And hello, Lazy Schema also. Okay, where were we? Yeah, so the reason that is, in case you want a reminder, let's just look at this algorithm again. We've got it somewhere around here. Yeah, here we are. So if we follow this through, okay, is this big enough? Yes, it is. if we follow this through, like let's say we take, so this is allowed to range over what numbers? Sorry, I'm still getting my head in the game. Assume the value of n is known, but m is allowed to range over all positive integers. Okay, so let's say that n is 5. And let's put that up at the top of the screen there. Gosh, window management is like about 80% of educating remotely, I think. Okay, that's going to have to do for now. N equals, say n equals 5, and m is that big number. What Knuth is saying is that after the first iteration, only the size of n is actually important. It gets bounded in some way. So let's perform this algorithm and see this at work. So let's say we do E1. In E1, we divide m by n and let r be the remainder. So we get something remainder, some number. Now, if we divide this number by 5, well, actually, if we take the remainder of it, rather, the remainder of dividing this big number by 5 is 4. We don't actually care about this number, but it's also quite long. In fact, I'll just tell you what it is. It's 10,600,000,000 something something something. Let me put it here. It's that. This reasonably large number. Is that actually true? Is that the right? I guess it looks approximately right. And I've lost the last digit now. There we go. 6. But we don't actually use this number for anything, so we can get rid of it. So we then, we have this property here, I guess. So R is 4. Then we ask in step E2, if R equals 0, the algorithm terminates, n is the answer, and R is not equal to 0. So we continue. And then in E3, we set m to n and n to R. And after this, m is equal to 5 and n is equal to 4 because the 4 is R. We just found that there. So after the first iteration, the size of m does not matter. Or, it matters, but it's not going to control the number of iterations we have in the algorithm. You may remember this, it may be elementary, but I need to get my head back into the algorithm, even if you don't. Okay, so continuing. But it is evident that after the, etc. So all we must do to find Tn, which is what we're asked to do. So basically the problem here, by the way, I should probably copy this over so that we can just get a picture for what the question is we're on track to investigate. That's kind of unhelpfully large. Okay, that's not helpful either. Okay, great. Let's have that. What's T5? So we're interested in T5, and we've got a procedure for T5 somewhere in the text. Yeah. All we must do to find Tn is to find the algorithm for m equals 1, m equals 2, m equals n. Count the total number of times step E1 has been executed and divide by n. So we could do that, but I guess we'll read on. Now, the important question is to determine the nature of Tn. Is it approximately equal to 1/3 n? Or square root n, for instance? Oh yeah, it's actually, yeah, I remember this. As a matter of fact, the answer to this question is an extremely difficult and fascinating mathematical problem, not yet completely solved, which is examined in more detail in section 453. For large values of n, it is possible to prove that Tn is approximately this number, or this, whatever this is. That is proportional to the natural logarithm of n. Yeah, so this is sort of surprising, I guess he's saying. Now, for this is for large values of n, so it's probably not going to work well for small values of n, so you shouldn't just plug it in. We should probably figure this out manually. Which we could do computationally. I haven't actually set up the stream to write code yet, so I'm kind of disinclined to do it by writing a program. Anyway, I'm just going to start seeing what we get. So let's say n equals 5 and m equals 0. How many steps do we get in that case? In that case, let's perform the algorithm. So it's step E1 that we're interested in. Divide m by n and let r be the remainder. So m divided by m mod 5 is 0. So r equals 0. E2 halts. So steps, so t, let's say t5, 0. Let's say that's 1 step. We should be able to notice a pattern here reasonably quickly, I should think. Okay, let's move my head out of the way. Actually, let's get rid of this stuff. Okay, we won't need that again, I don't think. Let's move that here. Great. Okay, so that's that case. Let's try with m equals 1. In this case, r equals 1. E2 does not halt. Let's say continue. We reduce and we set m equal to 5 and n equal to 1. In that case, we execute E1 again. So let's actually start marking this. So that we can count these later. E1, the remainder is going to be 5 mod 1, which is I guess wait, what's the remainder of 5 divided oh gosh, there's going to be so much of this. 5 divided by 1 is 5, so the remainder is 0. E2 halts, so T51 is 2. And I'm just going to swap these around to make this a bit easier to follow as we go through. Okay, so that's 2. Let's try this again with 2. In this case, the first time it's going to be a remainder 2. We're going to end up with 2 here. Now 5 mod 2 is 1. So we don't halt, we continue. M ends up being 5 in all cases after this. No, actually, wait. M gets set to 2. N gets set to 1. And we know where n equals 1, it's going to terminate next time round. So, because the remainder, if you divide 3 by 1, is going to be 0, and then E2 halts, which means T5 2 is 3. We really must set up a coding environment for the next stream. Okay. So that's 3. I feel like I need a bit more background noise. Let's get some rain in. Lexi T, it's scary, but your videos have helped me understand low-level programming much better and have the confidence to work through problems very close to the metal. That's great, Lexi T. Thank you. Thank you for saying that. I'm glad. Master XD, long time no see. How you doing? I'm doing well. Hello, Yanshifim. Hello again. Meadow Gamers, hi. But Jared Wilcott, hi. Or whatever is appropriate, an appropriate response to that emoji. Yeah, I'm doing good. I've got myself a black filter. The black filter is a fantastic way to get customer loyalty, in my experience, and that the moment you try it, you become adjusted to it. So it was a little treat for streaming today. Now, I once had made I say mistake, it was a kind of glorious mistake of ordering a black filter when I was in the United States of America earlier this year. I was in Arizona, and I was like, it was the European mind cannot comprehend moment, where they asked me, do you want small, medium, or large? And I was like, well, I usually get large, so I was like, large, obviously. It was like twice the height. It was bigger than my head. It was fantastic. Yeah, I had a great time. Yeah. Still think about that. If I could go back to exactly that place right now and get the same coffee, I would definitely do it. So if you run a coffee shop, it's a great idea to put that on your menu. But if you run a coffee shop, maybe you do run a coffee shop and you're not on your shift right now. Okay. M equals 3, N equals 5. So that's how I am, basically. Drinking coffee. Okay, remainder. If you divide 3 by 5. Mate, am I doing this right? 2 by 5. Okay. Yeah, M by N. Okay, 3 by 5 is 3, obviously. Sorry, I do, when I last studied maths, I did a bunch of like fake midterm papers, and I learned pretty well, but the big obstacle was I just made mistakes on the little things constantly. It was actually diabolical. Okay, so you'll see me double checking constantly, and just like, yeah. Okay. 5 by 3, remainder is 2. After this, we end up with 3 here and 2 here. And so we divide 3 by 2, which gets us a remainder 1. So we don't halt, we continue. E3, now M equals 2. N equals 1, and we terminate at this point, right? Because now remainder is going to be 0, and we terminate. And this is going to be 4, right? 1, 2, 3, 4. So we have a reasonably nice pattern, a pattern which is not currently appearing to have pi in it. So I don't know if we're going to have any surprises. Obviously it's, I hesitate even to open the. I'm gonna open the stats and see how it how it took 23 people. I feel like sometimes I feel like I'm my streaming, my channel is like an elaborate piece of like perverse performance art where you try to work out what is the most boring thing people will sit through, and Here we go. It's just like the old days. It's like humans computing things. We've gone full circle now. Anyway, but it is kind of like I would recommend sometime. I mean, at least I like to do this when I'm learning about, or I like to do it in general. If you do this stuff manually, obviously it is a bit dull, but you do gain a bit of an intuition that you wouldn't gain otherwise. I do this a lot with data analysis because I have had for a while a business focused job, and you have to work out things like, do you have problems with quality in what you're doing so that you can correct them. And you can just look at the graphs, right, which is great. But if you go through all of the data yourself without just letting the graph tell you what it wants to tell you, you often discover things. And so sometimes you do this here too. What it appears to be is that we've got 1, 2, 3, 4. So we're ending up with an escalating sequence. Now I should imagine at some point this will stop. But it might not stop with 5. It might just we might just end up with it cycling round, but we will see. Anyway, okay, so we're going to do it with 4 now. 5 mod 4 remainder is 1. Interesting. Yeah, so it is right, isn't it? M by n. So 3 by 5 is 3. 4 by 5 is... No, wait, I got that wrong. 4 divided by 5. The remainder of 4 divided by 5 is 4. It's not 1. That would be 5 divided by 4. Okay, so it is 4. I think. Okay, we swap these around, and so we get m equals 5, r equals 4. Now, when we do this, m by n, 5 by 4 is now 1. In this case, we get this being 4 and this being 1. This is going to be 0, of course, and so we terminate here. And so T5, 4 is actually three steps, is that right? Yeah. Yes, it is. It is right. Okay, so we end up with this one. So that's 3 now. So this is our sequence of increments has not continued. Now my intuition is telling me that once we get to this, now 5 mod 5 is 0. So we get essentially the same result as here. And in theory, if we continue going up, we get the same result as this. So, but actually we don't, because the inputs are going to be slightly different. Six mod 5 is 1 though. So we continue. So here we get m is 5 and n equals 1. So actually that is the same as this. So the value of m does not count after this point. Okay, and then the rest of it terminates like this. In which case, in theory for number 7, we should end up with the same as number 2. We should end up with the same answer. So let's find out, just check that that's the case. The remainder is definitely going to be 2, 5. So 7 mod 5 is 2. We continue. As a result, we get n equals 2. Yeah, and that's going to continue. That's going to complete in the same way. Great. Okay, so we've got the sequence. The sequence is... let me just... That's not helpful. That's not helpful either. Okay, let's take all this down. Okay, this is a bit more visible. Okay, so the sequence is 1, 2, 3, 4, 3. 1, 2, 3, and then we can, yeah, okay. So it's going to be this sequence forever, and we need to take the average over the size of the sequence, essentially. Now for that, that's one of those things where you work out like what it tends towards. I did this at some point in my history, but I do not remember how to do it effectively other than by computing it to a very large number and seeing what it seems to be moving towards, but let's try it, I guess. So in this case, well, actually, here's something we can do. We could add up all these. That's 1 plus 2 plus 3 plus 4 plus 3. That's 13. And that's 13 over 5 elements, so 13 over 5. Now, if we... actually, it's always going to be 13 over... no way, it might be different. It's probably going to tend... It's going to tend towards 13 over 5? I think it might. Because the only thing that's going to be different is where in this sequence we are at the end. So we might end up at like having one extra element. Oh no, wait. What are we trying to work out here? The average number of times step E1 is performed when n is 5. So it's actually going to be the average of these numbers, I think, which is it's just going to be 13 over 5. I think, to be exact, 2.6. 2.6 seems like a suspiciously nice number, right? It's probably 2.6 like feels like an answer. Okay, I'm not 100% on this. I'm not sure. But I mean, it looks right, doesn't it? Okay, I'm going to. I think we should. I think this seems like a useful opportunity to do one of those quizzes. This seems like I used to do this with Advent of Code, and it might be fun to do one now. Okay. Wow, it seems like making predictions is like a million. Wait, okay. Okay, I get it. Is... Okay. There you go. There's your chance to win some prizes or lose some prizes. Okay, looks like we're getting towards a solid prediction. Okay. Right, so we've got one. We've got we've got we've got one person. We've got 1% yes, 99% no. Okay, great. Okay. All right. Let's find out. Okay. 6, right? Let's not look at the. Let's not look at the any of the answers. Trying algorithm E with n equals 5 and m equals etc. For any q, so this is whatever the terms. This number of times, respectively. So the average is 2.6. I think the number 5 is 2.6. So it seems like yes wins. Okay. Okay. Okay, well, whoever you are, 1%, you well done. Thank you for the faith. All right. Oh, Lexi T, you're a good sport. Yanchi Film, I guess you were the 1%. Congrats. Okay, what else is happening? Yanchi Film earlier. Looking forward to the future roads videos. Me too. I I don't want to sound too much like a content creator, but I do work on them all the time. I've been doing like a lot of reading for the next big one. Yeah, which should be I'm excited for. 8PNG, it's going well. Thanks for joining. Lexi T, I'm struggling right now between the temptation to have AI solve little problems and do it myself, so I stay close to the actual algorithms. There's a lot of industry pressure to take the easy route. Yeah, 100%. It's yeah, it's difficult at the moment, I think, to know. Well, it's actually probably not difficult to know exactly what you need to do. You probably just need to be good at the AI tools. Is the reality of it? Like, I think it's you know, I was never really someone who worried about being left behind in my career so far, but the temptation is it's definitely a tempting feeling right now when you sort of take your eye off Hacker News for 3 minutes and then something else is new. Yeah, it's kind of it's a little stressful, but we're living through an interesting time, I think, and I do think, well, I should hope that all kinds of knowledge will be useful in the future. Part of my research, actually, I spend quite a bit of time with people who are very late in their careers, like retired, and it's an interesting experience seeing how people's careers have gone if they've fixed in a particular thing which went out of fashion versus if they didn't. They're generally fine, but it's probably wrong to say that they always. I think I don't think they ever regret it, but it's certainly not a great career move to not move with the times. I don't know what I'm saying. Kind of silly, but yeah, it feels like you've got to know the AI tools, but these things are still interesting and useful to know about, and you would hope, right? You would think that they help with debugging skills. In any case, yeah, and you know, it does well. Yeah, I think I have. That's all the insight I have on that at the moment. All right, so that was question 6 completed in the most manual way possible. HM21. So this one is probably going to be one I can't do because HM stands for higher maths, higher mathematics. Let UM be the average number of times that step E1 is executed in algorithm E. If M is known and n is allowed to range over all positive integers. Show that um is well defined. Is um in any way related to tm? Oh, so this is the situation in which, so here is the situation where n was defined, the thing which we're going to divide by and take the remainder of. That's the thing that allows us to do all of the work we previously did. is the average number of times in the opposite case, where m is known and n is allowed to range over all positive integers. So there's not a sort of bounding effect there in that case. I don't know what well defined means. I suppose it would mean it's not, like you could write a formula for it or something. And is it related to tm? Now, if we were going to, I'll just sort of talk around this and see if I get anywhere, like a starting point. Or maybe I won't. Let me see. Let me take a look at this. Okay, so the thing. Now let's say we had a very large, let's say we have a very large. We previously looked at the situation in which we have a very large m. And in fact, let's create another area for this. Yeah, well, we had a very large m and a small n, and we looked at the fact that it doesn't matter how large m is, because it's going to be divided by 5, and we're going to take the remainder, so the remainder will be at most 5, so these will then get swapped over, and so we'll end up with a reasonably short iteration cycle. But in the other case, let's just try it out. In this case, we divide 5 by whatever this big number is, and we take the remainder. And we get, after E1 we get R is 5. Now Y is, that is the case, because, and that's going to be the case for most m's up to this. So even if we had like this number, the remainder is going to be 343. Let's try it with 5 though, because if we're trying to take the remainder of m divided by n, then it's going to have to get up to this number before we get back to a remainder of 0. So the maximum remainder we can get, I think, is this. And that's just going to be this number again. So E2 doesn't terminate, so E2 can't. E3 is then going to be, m is set to this, and then n is set to 5. And then after this, the remainder is going to be 2. Then E2 continues, E3, we say that n is 5 and r is 2. And then it's like we know the continuation of that, because we've done it up here, I think. Sorry, this is actually going to be m is 5 and n is 2. Well, we've got that somewhere, I think. We've got it here. So that's actually going to be 1, 2, 3, 4. I think. So that doesn't seem like totally unmanageable. I guess it would get more difficult if we had something that was some reasonable fraction of this. So let's say if we had that number. In this case, really what's determining the number of steps in this algorithm is how quickly R declines. And that's determined by, well, it's just determined by the remainder. If we divide one by the other, probably. No, I mean that's not exactly true. But there's like that's the kind of thing we're looking at. How quickly these things turn down to small numbers, and then we get to small numbers. It's a small number of steps, inevitably. I think. So, in the case where m is known, n is allowed to range over all positive integers. If we were to try to put this in terms of m, yeah, because it's, let me actually put this in here. Okay, so n is allowed to range over all positive integers, m is known, and so we want to put this in terms of n. Yeah, I would be tempted to write a program for this, I think, to try to explore it. Let's say if we know that m is 1, maybe there's a kind of trivial answer to this. So if we then had 1 here, gosh, okay, let's try this. Now in this case, E1 R is 1, so it's going to be 0, so E2 terminates. So U U11's going to be 1. In this case, E1, the remainder is 1 mod 2, which is 1. E2 continues. M equals 2 and n equals 1. we have 2 mod 1 is 0, and then we are able to terminate. So u12 is 2. Then with this, I think the remainder is going to be, no, actually it's 2. It's 2, then E2 continues, E3, we've got M equals 3, and N equals 2. E1 is going to be 3 mod 2, which is 1. So E2 continues, and E3, we're going to have M equals 2, and N equals 1, which we've got this for. And so this then terminates. And so U13 is 1, 2, 3. This presumably doesn't continue forever. That wouldn't make any sense, so it's probably not going to continue forever. But it feels like a problem we might be able to puzzle out. But I think we're going to need a computer for it in order for it to not be like super arduous. So I think I'm going to come back to that one. Yeah, let's say 7. Well, you would assume, right? You think I've made a mistake in which one, Yan Shifeng? I missed the time that was. In any case, probably it is related. Might not be, but probably if we're given that hint, probably it is. So I think I might come back for that one. Come back to that one. What's the next one? Give an effective formal algorithm for computing the greatest common divisor of positive integers m and n by specifying those 3 values. Give an effective formal algorithm for computing the greatest common divisor of positive integers m and n by specifying those and those and those. Let the input be represented by the string am bn, that is, MAs followed by NBs. Try to make your solution as simple as possible. Hint, use algorithm E, but instead of division in step E1, set R to be the absolute value of m minus n, and n be the minimum of those two. Well, that makes sense. Effective has a specific meaning here, right? We were given it earlier. It's somewhere in here. No, it is in chapter 1, now I think of it. Where is it? Where is it? Where is it? Effective. Ugh, I'm going to search for it. Where is it? Here it is. Okay. Right. An algorithm is also expected to be effective in the sense that its operations must all be sufficiently basic that they can, in principle, be done exactly and in a finite length of time by someone using pencil and paper. Algorithm E uses only the operations of dividing one positive integer by another, testing if an integer is 0, and setting the value of one variable equal to the value of another. These are effective because they can be da-da-da. So I think it means they need to be like precisely specified. I'm probably not yeah, I'm probably not going to be able to get this 100% right, but I think I can have a good go at it. Give an effective formal algorithm for computing the greatest common divisor of positive integers m and n by specifying these values as in equations 3. Let the input be represented by the string. String has some meaning here. A sequence of symbols. Okay, so it's like it's trying to get us to construct some sort of automata type thing. Okay. And then it's given us some like more effective way, I guess, of trying to work this out. Now, is this something I can feasibly do? Okay. Q is a set, I guess, and omega are subsets of Q. F is a function. Then he says something about strings elsewhere. Yeah, what does he say? Yeah, yeah, okay, so he's talking about effectiveness here. The formulation of the concept of an algorithm does not include the restriction of effectiveness. This formulation does not include this restriction of effectiveness mentioned earlier. For example, Q might denote infinite sequences that are not computable by pencil and paper methods, or F might involve operations that mere mortals cannot always perform. So I guess he's making the point that yeah, Q, which is a set of something, might denote infinite sequences. So I guess we might get an infinitely sized number, which, you know, could not be effective because it could not be computed in a finite amount of time. Yeah, and F might include operations that mere mortals cannot always perform. Remainder is like, I don't know if that's well defined enough. So he's giving us a way that we can define this in a more effective way. Only elementary operations are involved. We can place restrictions on these. For example, as follows. Let A be a finite set of letters, and let A star be the set of all strings on A, the set of all ordered sequences x1, x2, xn, etc., where n is greater than or equal to 0 and xj is in A for whatever. When n equals 0, this notation stands for the empty string. In general, it stands for a string of length n. The idea is to encode the states of the computation so that they are represented by strings of A star. Now let n be a non-negative integer, and let q be the set of all... is that theta again? No, it's not. What is that one? I'm going to have to do some flashcards for these. Sigma. Where sigma is in A star and j is an integer, etc. Let I be the subset of Q with J equals 0, and let I think that's omega. Let omega be the subset, blah, blah, blah. No, it's not. It doesn't make any sense to me. Okay, let's consider this set of exercises complete to my current skill. My hunch is I'm probably going to want to come back to these after having read or worked through the book of proofs, and then probably also having worked through concrete mathematics, I think is Knuth's other book, where he gives a lot of the mathematical foundations for this type of thing. So probably come back to those after that. Let's look at M30, which I will also not be able to do. Suppose that C1 computational methods, C1 might stand for Algorithmic, except that M and N are restricted in magnitude, and C2 might stand for a computer program implementation of Algorithmic. Thus, Q2 might be the set of all states of the machine, i.e. all possible configurations of its memory and registers. F2 might be the definition of single, etc., whatever. Formulate a set theoretic definition for the concept C2 is a representation of C1, or C2 simulates C1. This is to mean intuitively that any computational sequence of C1 is mimicked by C2, except that C2 might take more steps in which to do the computation, and it might retain more information in its states in order to make this thing make sense. Okay, I'm not going to do that either. Okay, so we've gotten through maybe the first 6, which is probably better than I expected, honestly. We've not proven this, but we got close to a proof. I'm going to learn about proofs to do that. We didn't get that, or this, but that's fine. We kind of knew that would happen. Your first E1 step of M equals 1, N equals 3 is incorrect. Okay. 1 mod 3. Oh yeah, true. That's true. So in that case, this would be M equals 3, N equals 1. Okay, so we would get... Is it always that? The greatest common divisor of 1 and another large number, in theory, probably should only ever take one step. Should we say that's true? Let's try that. Oh, no, wait. Yeah, well, yeah. So it's always going to be that, and then, yeah. Okay, so in this case, if M is known and M is 1, then it's always going to be one step. Okay, well, we've solved the easiest possible case, which I guess was the original point. Thank you, Janshifin, for pointing that out. Yeah, probably there's another way of muddling around with that as well, either with a program. Might play around with it with a program next time, once I've got a programming environment set up. But it's labeled HM, so probably it's going to be fairly. It's going to require some knowledge that I've not got at the moment. Okay, what else is going on in chat? Shushi Thrash. This is The Art of Computer Programming by Donald Knuth. It's like it's sort of an attempt to write down all of computer science. I think that was probably that was his original attempt. Yeah, if you love coding, what you love about coding may not come up in this book necessarily. I've actually had some comments on YouTube. In case you're watching this from YouTube and you're thinking, I don't know anything about programming, but maybe I'll start with this book. That might be a good idea if you are pretty good at mathematics already. If you're not, it's going to be basically impenetrable, I would say. Unless you want to, really go through, if you've got like an amazing, brain and ability to work through two quite new topics at once. But yeah, probably not the right place to start. But if you want to get into some of the maths and computer science of computing, and you're a reasonably confident coder, then it's definitely an interesting thing to spend some time with. Exonyam, nice to catch you live. Thanks. YouTube business, yeah, I know. I put up the VODs on a second channel, but I am working on main channel videos still. But yeah, they're taking a while. I've put myself forward for a talk at a fourth meetup next week, so I might post something out of that too. Okay, all right. So I think my brain has computed enough now. So let's spend some time with the text. Now it says mathematical preliminaries here. This could also be another. I think this book starts fairly math heavy, and then it may get more computer heavy. I think Yanchifim, in fact, you said that last time. So I think this probably will be the most math heavy chapter, so maybe a rough one for me. But we will see. Let's get through it. Let me move it around. Okay. In this section, we shall investigate the mathematical notations that occur throughout the art of computer programming, and will derive several basic formulas that will be used repeatedly. Even a reader not concerned with the more complex mathematical derivations should at least become familiar with the meanings of the various formulas, so as to be able to use the results of the derivations. I'll turn that down a little bit. Mathematical notation is used for two main purposes in this book: to describe portions of an algorithm and to analyze the performance characteristics of an algorithm. The notation used in descriptions of algorithms is quite simple, as explained in the previous section. When analyzing the performance of algorithms, we need to use other more specialized notations. Most of the algorithms we will discuss are accompanied by mathematical calculations that determine the speed at which the algorithm may be expected to run. These calculations draw on nearly every branch of mathematics, oh goody, and a separate book would be necessary to develop all of the mathematical concepts that are used in one place or another. However, the majority of the calculations can be carried out with a knowledge of college algebra, and the reader with a knowledge of elementary calculus will be able to understand nearly all of the mathematics that appears. Sometimes we will need to use deeper results of complex variable theory, group theory, number theory, probability theory, etc. In such cases, the topic will be explained in an elementary manner if possible, or a reference to other sources of information will be given. The mathematical techniques involved in the analysis of algorithms usually have a distinct flavour. Let me read that again. The mathematical techniques involved in the analysis of algorithms usually have a distinct flavour. For example, we will quite often find ourselves working with finite summations of rational numbers, or with the solutions to recurrence relations. Such topics are traditionally given only a light treatment in mathematics courses, and so the following subsections are designed not only to give a thorough drilling in the use of the notations to be defined, but also to illustrate in depth the types of calculations and techniques that will be most useful to us. Important note: although the following subsections provide a rather extensive training in the mathematical skills needed in connection with the study of computer algorithms, most readers will not see at first any very strong connections between this material and computer programming, except in section 121. The reader may choose to read the following subsections carefully with implicit faith in the author's assertion that the topics treated here are indeed very relevant, but it is probably preferable for motivation to skim over this section lightly at first, and after... I love that he's italicized this section. He's probably had people saying to him, wow, it's pretty maths heavy. To skim over this section lightly at first, and after seeing numerous applications of the techniques in future chapters, return to it later for more intensive study. That's how I'm imagining him saying that. If too much time is spent studying this material when first reading the book, a person might never get onto the computer programming topics. However, Each reader should at least become familiar with the general contents of these subsections and should try to solve a few of the exercises, even on first reading. Section 1 to 10 should receive particular attention since it is the point of departure for most of the theoretical material developed later. Section 1.3, which follows at 1.2, of course, I don't know why that is mentioned. Maybe he skips sections sometimes, I don't know. Abruptly leaves the realm of pure mathematics and enters into pure computer programming. Okay. Oh, we're in 1.2 now, so I guess he's saying we're going to get to it soon, don't worry. Okay. A more leisurely presentation of much of the following material, together with related concepts, can be found in the book Concrete Mathematics, which we will also be reading, by R.L. Graham, Knuth, and Patashnik, second edition, etc., etc., etc. That book will simply be called CMath when we need to refer to it later. Okay, mathematical induction. Now, I will say, so I was thinking about this earlier. Just worth note. I think in a way, one of the benefits sometimes, well, as a one thing educators are very fond of saying, they're educators are very fond of playing two roles. One is the role of the expert, where they're like, of course, well, I know all this stuff, so I can help you with this. The other is the role of the naive person, where they say, because I don't know it, I'm going to be even better at educating you. And of course, it's difficult to play both roles at once. So you should know a bit about my experience in mathematics if you haven't already got that. If you've been struggling through watching me struggle through this for an hour, I have, I guess, what in the US would be sub-high school mathematics. In the UK, I did my mathematics GCSEs, in which we cover essentially like what I would guess is algebra. I'm not like 100% sure on that, but you can like solve equations. We did inequalities there, but if you recall last time, my inequalities are a bit rusty. And at A level, which is like 16 to 18, I studied mathematics and further mathematics. And I also did statistics at GCSE as well, which is quite useful, but maybe not 100% relevant here. And so I've done some calculus. I think it's single variable calculus, but I don't even know enough about calculus to say whether it's single variable. I've done some differentiation and integration. I know roughly what they are for. I couldn't do them again right now, but I know that there are methods that I can look up. I've never proven anything in my life. I've never proven anything. I've never induced, in these terms. Those things were not introduced to me at A level. So what I have is basically like as if you're a self-taught engineer without a numerate degree. It's like what I have. Self-taught software engineer. So hopefully what I have to learn here will be a good like minimum you would expect from a software engineer. And so by me learning this here, you may have the opportunity also, if you don't have the knowledge already, to learn it yourself. And if you do have it, maybe it'll be funny. Maybe it'll be funny, maybe it'll be frustrating. In any case, I don't really put myself down by that. I don't mind not knowing things. But if you want, like if you're expecting these things to make sense to me at first, that's why they don't. Let Pn. Okay, so we're going to talk about mathematical induction. I think induction is important. I've got like a big flashing light in my head saying induction is important, probably for proving things. So, yeah, I think this is going to be an important section. Let Pn be some statement about the integer n. For example, Pn might be n times 3, n plus 3 is an even number. Okay. So we've got a statement which is applied to a certain number. Or if n is greater than or equal to 10, then let 2 to the power n be greater than n cubed. Suppose we want to prove that Pn is true for all positive integers n. Okay, so we're into proving things. An important way to do this is give a proof that P1 is true, give a proof that if all of P1, P2 through to Pn are true, then Pn plus 1 is also true. This proof should be valid for any positive integer n. Well, okay, that's, full stop. So we need to do these two things. I guess that's mathematical induction, probably. Since we're moving to an example, we can assume it is. As an example, consider the following series of equations, which many people have discovered independently since ancient times. 1 is 1 squared, 1 plus 3 is 2 squared, 1 plus 3 plus 5 is 3 squared, etc., etc. We can formulate the general property as follows. 1 plus 3 plus sequence continues plus 2n minus 1 is n squared. A sum of n terms or something. Let us for the moment call this equation Pn. We wish to prove that Pn is true for all positive n. Following the procedure outlined above, we have P1 is true since 1 is 1 squared. If all of P1 through Pn are true, then in particular Pn is true. So equality 2 holds. Adding 2n plus 1 to both sides, we obtain this thing. 1 plus 3 plus... yeah, fine. Okay, so we're describing a procedure here. I guess a proof is a kind of procedure. Like it's a thing you... well, procedure. Oh, it uses the term procedure here. So I guess it is a procedure. Which proves that Pn plus 1 is also true. Somehow this proves that Pn plus 1 is also true. In some way, it does. Pn is true for all positive n. Okay, wait. I'm going to have to come back to this. Or something. We can regard this method as an algorithmic proof procedure. In fact, the following algorithm produces a proof of Pn for any positive integer n, assuming that steps A and B above have been worked out. Algorithm 1, I assume it's 1, construct a proof. Given a positive integer n, this algorithm will output a proof that Pn is true. Okay, first we prove P1, set k to 1, and according to A, output a proof of P1. A is this, I guess. K equals n question mark. If k is n, terminate the algorithm. The required proof has been output. Then prove pk plus 1. According to B, output a proof that if all of P1 to Pk are true, then Pk plus 1 is true. Also output, we have already proved, etc., 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 hence, okay, increase k by 1. And so this is some sort of algorithm for mathematical induction. So I think what he's saying here is, first you have to prove P for 1. Then you have to prove P for n plus 1 all the way up to k. maybe. And then you prove that... I don't know where you go after this. I guess the proof is done. Since this algorithm clearly presents a proof of Pn for any given n, the proof technique consisting of steps A and B is logically valid. It is called proof by mathematical induction. I don't think he's, yeah, he's sort of like, he's got a few things in here. He's got this particular thing, which he's using as an example of a thing he wants to prove. He's also talking about how mathematical induction works, which is this. That's mathematical induction. This is not related to this at all. These are just two things we need to do if we want to prove that Pn is true for all positive integers n. And n, I guess, is... would we say this is a set, maybe? Maybe we would. It's a category of things, not in a rigorous mode. I'm not using that term rigorously. So this is mathematical induction. And then he's got this algorithm, which is for constructing a proof. So this is a proof by mathematical induction. This is mathematical induction. This is an example of it. I think this is probably not... This is probably useful if you want to write proofs yourself. Like, this is how you might do it. But probably this wouldn't usually be put as an algorithm. He's probably doing that to be Knuthy. Okay. Okay. I think although I don't understand exactly what he's putting here, like I don't really get how this step works, which proves it doesn't prove it to me. So probably if I stared at this long enough, it would prove it to me. I guess maybe it's a proof. It's proved because these are like they have a correspondence to each other in some way. Let's say that's true. So he's trying to say this is proof by mathematical induction. The concept of mathematical induction. In fact, before I move on, let's see if chat is. Let's see what chat is saying. Okay. All right. Induction, the hand wave of mathematics. Okay. Statistics super useful. Yeah, I found statistics really useful. The last proper mathematics learning I did was statistics as well, based on a Stanford course, which I guess is also working with this. Induction, super useful foundational tool. Says check 94. I believe you. If you can get onto rung one of the... This is from Yanchifin. If you can get onto rung one of the ladder and you can get from rung n to rung n plus 1 for any n, then you can get onto any rung you like. Yeah, this makes sense. Check 94 says, this is a curious mix of strong and weak induction. Prove that k plus 1 follows from k. Or better yet, prove that pk plus 1 follows from p0 and pk. Recall what Pn actually states. Let's do that. Okay. All right. I get the gist. I get it in the sense that if I was in a lecture, I would be able to, I would leave the lecture feeling like, oh, okay, kind of makes sense. And then I would like hit my head on the exercises and have to relearn it all over again, which is a kind of learning, though it is, yeah, it will fall apart reasonably quickly, but that's in a way good. Okay, the concept of mathematical induction should be distinguished from what is usually called inductive reasoning in science. A scientist takes specific observations and creates by induction, a general theory or hypothesis that accounts for these facts. For example, we might observe the 5 relations in 1 above and formulate 2. 1 above is this, I guess. 5 relations. Let's say there are 5 relations. And formulate 2. That's the same place. Oh, okay, wait. These. 1 and 2. And formulate 2. In this sense, induction is no more than our best guess about the situation. Mathematicians would call it an empirical result or a conjecture. Another example will be helpful. I'll be the judge of that, I think. Let Pn denote the number of partitions of n, that is, the number of different ways to write n as a sum of positive integers disregarding order. Since 5 can be partitioned in exactly 7 ways, that's these, we have P5 equals 7. In fact, it is easy to establish the first few values. Makes sense? At this point, we might tentatively formulate, by induction, the hypothesis that the sequence P2, P3, etc. runs through the prime numbers. To test this hypothesis, we proceed to calculate P6, and behold, P6 equals 11, confirming our conjecture. Square brackets. Unfortunately, P7 turns out to be 15, spoiling everything, and we must try again. The numbers Pn are known to be quite complicated, although I need to work out how to pronounce his name, Ramanujan. This guy, I feel like I once read an article about genius, which was basically mainly about this guy, I think. Yeah, anyway, so apparently this guy is he's a real character. Like sort of genius. And assuming it's the same one, could be same name. Succeeded in guessing and proving many remarkable things about them, although it does sound like him. And there's a book about him here, so I guess it probably is him. Mathematical induction is quite different from induction in the sense just explained. So basically what he's saying here is, I think, you could look at these and formulate by induction, by the sense of induction, which is induction, which is like the sun rose yesterday and all the days before, so probably it's going to rise, I guess. That would be a form of induction in science. It's an empirical sort of process, but it's different from mathematics. Mathematical induction is quite different from induction in the sense just explained. It is not just guesswork, but a conclusive proof of a statement. Indeed, it is a proof of infinitely many statements, one for each n. It has been called induction only because one must first decide somehow what is to be proved before one can apply the technique of mathematical induction. Henceforth, in this book, we will use the word induction only when we wish to imply proof by mathematical induction. Okay, that's fine. I can live with that. There is a geometrical way to prove equality. Is it equality? I think it's equality. Equality 2. Or equation. Could be equation. Figure 3 shows for n equals 6, n squared cells broken into groups of 1 plus 3, etc., 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 up to 2n minus 1 cells. So this is like a proof in the sense, it's like a visual proof, I guess. Like the reason this is a proof is because we can see it's a square, I guess. Like you can see this we've got this square, and I guess we're saying it's a square because we're adding a row and a column on. And I guess we can say 2n minus 1. So we're saying, I mean, it's pleasing, right? Because you can understand it. Because you can understand it at all. Probably, if you knew this, you would understand the equations better. But it's pleasing for me because you've got your one along the top, 1 on the side, that's n, minus 1 because we've got a little bit of an overlap here. So I guess that's like we can sort of look at it and see that it will apply for all of the numbers, all of the squares that we can make in this way. But I guess what he's about to say is this is not a sufficient kind of proof because some reason I don't know. I mean, I would struggle to, like, if I was wanted to call this a proof, I'd be like, look, look, that'd be my proof. But I go, look at this, it proves it. But I wouldn't feel very confident. Okay, anyway, however, in the final analysis, this picture can only be regarded as a proof if we show that the construction can be carried out for all n, and such a demonstration is essentially the same as a proof by induction. So I guess he's saying it like reduces back to the same sort of work. Okay. Yeah. What's chat saying? Okay. And forgetting and having to relearn is also a part of learning. You seem to have a pretty good mathematical intuition for what I can see. Definitely don't put yourself down. Thank you. Yeah, I mean, we will see. I will be proven by, what is it that they say? I'll be proven by fire? Something like that. 10x engineer. Com, thanks for joining. Yeah, the rain sounds are mostly to keep me focused, but you may also enjoy them. There will be other sounds, not today, but in future. Akashiv KVD. Maths feels so difficult to get back into after being years outside of uni. Yeah, I know. Welcome, Infected Research. Great name. Proof, look. Yeah. just look at it. Yeah, just look at it. Just see it. What's the program on the screen? So on the, I guess, right-hand side of the screen is the Mac preview app with a PDF in it. On the left-hand side, which is not really relevant to what we're doing now, it is Excalidraw, which should also answer some YouTube comments as well. I go back and forth between Excalidraw and TLDraw. Both are worth trying. I think they both have different strengths and weaknesses. Excalidraw is kind of nice for this at the moment, but I think I probably will find something a bit more special purpose. Meaning there's something called Excalidraw. There's like a math version of it, which I'm probably going to do at some point because I'm going to need to be able to put proper. You can't just have like use the ASCII for everything, probably. Okay. And a coding environment. Next time. Okay. Our proof of equation 2 can be used only a special case. Sorry, our proof of equation 2 used only a special case of B. We merely show that the truth of Pn implies the truth of Pn plus 1. This is an important simple case. This is an important simple case that arises frequently. But our next example illustrates the power of this method a little more. We define the Fibonacci sequence f0, f1, etc. by the rule that f0 equals 0, f1 equals 1, and every further term is the sum of the preceding two. Well, that's something I can understand. Thus the sequence begins 0, 1, 1, 2, etc. We will investigate it in detail in section 128. We will now prove that if theta, British theta, is the number 1 plus the root of 5 over 2. Wait, where's theta come from? Where's theta? How did theta get in here? Is he using theta in like a well-known sense? Like is it something? No, it's phi. It's not theta. Oh my gosh. Is it phi? I think it's pronounced that way. It's the golden ratio. It's golden ratio. Phi. Yeah, golden ratio. Okay. If phi is 1 plus the root of 5 over 2, we have fn is less than or equal to phi to the power of n minus 1 for all positive integers n. Call this formula Pn. If n equals 1, then f1, which is going to be less than this number, f1 equals theta to the power 0 equals, sorry, not theta, phi equals phi to the 0. Okay, so we're going kind of the opposite way here. We're saying, wait, f1? Where is he getting this from? f1 equals 1 equals phi to the 0 is phi to the 1 minus 1. Okay, so step A has been done. Step A is like the one where it's equals 1, so the first step. For step B, we notice first that P2 is also true, since F2 is equal to 1 is less than phi to the 1 which we just notice. Now, if all of, what is the golden ratio again? It's 1.618. Yeah, so 1 is less than 1.618, which makes sense. Okay, now if all the etc. are true and n is greater than 1, we know in particular that Pn minus 1 and Pn also are true. So Fn minus 1 is less than or equal to phi n minus 2. And this is also, adding these inequalities, we get this thing here. The important properties of the number phi, indeed the reason we chose this number for this problem in the first place, is that 1 plus phi is equal to phi squared, which is probably a property of that number, a special property of it. Plugging 5 into 4, oh, he's labelled these on the right, need to remember that. 5 into 4 gives this, which is this, so step B has been done, and 3 has been proved by mathematical induction. Okay. If you say so. Notice that we approach step B in two different ways here. We proved that Pn plus 1 directly, we prove this directly when n equals 1, and we use an inductive method when n is greater than 1. This was necessary since when n equals 1, our reference to Pn minus 1 equals P0 would not have been legitimate. Actually, P0 does happen to be true in this particular context, but we weren't asked to prove it, so we didn't. Mathematical induction can also be used to prove things about algorithms. Consider the following generalization of Euclid's algorithm. That's the one we were looking at before, I think. Okay, given two positive integers m and n, we compute their greatest common divisor d, and we also compute two not necessarily positive integers a and b, such that am plus bn equals d. Okay, and so we perform this algorithm. Oh yeah, oh wait, okay, wait. So this is an algorithm. So we set these numbers. We set this, we've got this thing here, which denotes some variant of, I guess. And we set these to 0. And we set C to something and Dn. Why are we doing this? I guess this is somehow useful. Oh wait, okay, so we're trying to compute what we multiply these things by. Or are we? No, we're not. That's just there for some reason. Let Q and R be the quotient and remainder respectively as C divided by D. The algorithm terminates. We have in this case A M B N equals D as desired. Then we do a bunch of recycling. Horrendous. And then go back to E2. If we suppress the variables A, B, A quote and B quote from this algorithm and use M and N for the auxiliary variables C and D, we have our old algorithm 1 plus 1E. Okay. Oh yeah, from section 1.1, I remember. The new version does a little more by determining the coefficients A and B. Suppose that M is this and N is this. We have successfully, after step E2... Whoa, okay. Weird stuff happening in my preview. Yeah. We've got this table. Right, so we're... Whoa, okay. What on earth is going on there? I think it's trying to put this as a phone number. It's not a phone number. Okay. Okay. 5 times this minus 16 times this is this by this equals 29, the greatest common divisor. I'm sure it must be obvious what the utility of this is. Maybe somebody's saying. Okay. It's also known as Erebata's Kutaka algorithm. Helps you compute the coefficients in Bezout's identity. You can use it to compute the multiplicative inverse of number S modulo A number T, as long as GCD. Okay, great. Thank you, Flofi. Andrew says, not obvious at all, don't worry. It is very useful, mostly for solving integer equations, which is distantly related to cryptography. Okay. Well, that's useful to know. Okay, so let's say we got this algorithm for some reason. The problem is to prove that this algorithm works properly for all M and N. We can try to apply the method of mathematical induction by letting Pn be the statement algorithm E works for N and all integers M. However, that approach doesn't work out so easily, and we need to prove some extra facts. After a little study, we find that something must be proved about A, B, A quote and B quote, and the appropriate fact is that the equalities these things always hold whenever step E2 is executed. We may prove these equalities directly by observing that they are certainly true the first time we get to E2, and that step E4 does not change the validity. Okay. Now we are ready to show that algorithm E is valid by induction on N. If M is a multiple of N, the algorithm obviously works properly, since we are done immediately at E3 the first time. The case always occurs when N equals 1. The only case remaining is when N is greater than 1 and M is not a multiple of N. In such a case, the algorithm proceeds to set N to C, or C to N, D to R after the first execution, and since R is less than N, we may assume by induction that the final value of D is the greatest common divisor of N and R. By the argument given in section 1.1, the pairs Mn and Nr have the same common divisors, and in particular, they have the same greatest common divisor. Hence, D is the GCD of M and N, and AM plus Bn equals D by 6. Okay, the italicized phrase in the proof above illustrates the conventional language that is so often used in inductive proof. When doing part B of the construction, rather than saying we will now assume P1, P2, Pn, etc., and with this assumption we'll prove Pn plus 1, we often say simply we will now prove Pn. We may assume by induction that Pk is true whenever 1 Kn. 1 is in, K is in the range, I guess. 1 and N. Okay, we've got some diagram here of some kind. the flowchart. Okay, how long we got left in this particular section? I think my brain needs a break. Okay, I'm going to take a short break there. I'll be back in. Let me check out the chat before I do. Yeah, Knuth is trying to learn you some number theory. Okay, he's not doing a very good job so far, but I will come back to this and I will understand it. I think one of the things I'm doing in this is also just keeping track of when I cover certain things, so that at some point later I'm going to come back and observe myself failing to understand them and have a good laugh about it. Feels like a very hardcore starting point for a chapter called Mathematical Prerequisites, yeah. Check 94 says, there's also a handful of number theoretical tools that are inescapable in computability and complexity theory. That does seem true. Fluffy says, I think the prerequisite is mostly the induction and less the number theory. Having a good instinct for number theory does help with algorithms because you get a feel for the asymptotic, I think that's how you pronounce that, behavior of recurrence relations though, but this specific algorithm probably doesn't give you that. I'll have to take your word for it at this point, but I'm excited when all this stuff feels reasonably obvious to me. All right, I'm going to take a short break. We're at 1 hour 40. Take a short break, and I will come back in about 5 minutes. So enjoy. I'm going to turn up the rain noise until then. There we go. I'll be back. Hello again. Let me know if the rain noise is too loud at any point, of course. Let me turn up my own audio, actually. That probably would help me determine. Yeah, okay, that's better. Right. How am I sounding? Okay, that's a bit loud. Let's turn off myself. Okay. All right. Well, you know what I think? I'm reflecting. As I've warned you, I won't labour the point, but as I've warned you, we're getting to the point now. We're getting to a section that my mathematical abilities are insufficient to parse the text properly. So what I'm going to do is we're going to work through this. We're going to just breeze through this reasonably quickly. I'm going to take a look at, well, let's just gloss over where we get to with this. Yeah, we get to the exercises, and is this purely on mathematical induction? Oh my gosh. Okay, all right. Okay, and then there's a whole other section on logarithms. Let's go to the contents, actually. The contents will probably tell us more. Okay, all right. Okay, all right, so there's a lot of preliminaries. So we're going to be working through these for a while. Okay, fine. That's fine. All right. So a plan is emerging in my mind. So I think what I'd like to do with each of these is to come up with, before we move on to, because we're going to get through to programming stuff at some point. So the point isn't to focus only on the parts that I can already parse. I do want to get a feeling for some of these topics. So I'm going to read through the mathematical induction part reasonably swiftly, just being aware that I'm probably not going to get a lot of it. Then take a very brief look at the exercises, probably not try too many, and then I think we're going to switch to some specific proof-related topics, which will probably involve looking at book of proofs. And then we'll go through these, and hopefully they won't take quite as long as it will for me to get to grips with mathematical induction. And then, well, it'll be a while before we get through all of that. But when we do, we should have a reasonably good base for the rest of the book. He does, of course, emphasize we shouldn't let ourselves be too blocked by it, but I think I want to get the basic ideas at least. Okay, anyway, so where were we? Yeah, we were here. Okay, fine. If we examine this argument very closely and change our viewpoint slightly, we can envision a general method applicable to proving the validity of any algorithm. The idea is to take a flowchart for some algorithm and to label each of the arrows with an assertion about the current state of affairs at the time the computation traverses that arrow. See figure 4. That's these. Wait, okay, so what's he saying here? The idea is to take a flowchart for some algorithm and to label each of the arrows with an assertion about the current state of affairs at the time the computation traverses that arrow. Well, that's an interesting idea. Okay. So, fine. So he's sort of saying that if we want to, like, he's trying to kind of take us, or take, in theory, us, suppose we had a basic understanding of mathematical induction. He's trying to take us from mathematical induction to how do we apply mathematical induction to prove the properties of, or analyze the properties of algorithms by using this approach. So the idea is that we assert the properties at the start, or we prove the properties at the start, if we like, and then we should be able to take each step and kind of modify the properties we know about, and then do this at every step, and then in theory we should be able to work out where the stopping point is and then prove where we end up, which is an interesting idea. Should be fun to be able to do that. Okay, see Fig 4 where the assertions have been labelled A1, A2, A6, etc. All of the assertions have the additional stipulation that the variables are integers. This stipulation has been omitted to save space. A1 gives the initial assumptions upon entry to the algorithm, and A4 states what we hope to prove about the output values A, B, and D. That's this. The general method constructs a proof for each box in the flowchart that if an assertion attached to any arrow leading to the box is true before the operation in that box is performed, then all of the assertions on the relevant arrows leading away from that box are true after the operation. Thus, for example, we must prove that either A2 or A6 before E2 the step E2 implies A3 after E2. Wait, okay. We must prove that either A2 or A6 before E2, that's A2 or A6 because those are the steps leading into E2. So we have to prove both because it's got two places we can go into it. Implies A3 after E2. In this case, A2 is a stronger statement than A6. That is, A2 implies A6. So we need only prove that A6 before E2 implies A3 after. Okay, whatever. Notice that the condition D is greater than 0 is necessary in A6 just to prove that operation E2 even makes sense. It is also necessary to show that A3 and R equals 0 implies A4, that A3 and R not equals to 0 implies A5, etc. Each of the required proofs is very straightforward. Once statement 7, that's this, has been proved, for each box it follows that all assertions are true during any execution of the algorithm. For we can now use induction on the number of steps of the computation, in the sense of the number of arrows traversed in the flowchart. While traversing the first arrow, the one leading from start, the assertion A1 is true, since we can always assume that our input values meet the specifications. So the assertion on the very first arrow traversed is correct. If the assertion that labels the nth arrow is true, then by 7 the assertion that labels the n+1st arrow is also true. So I guess this is probably what people mean by proving algorithms, probably something like this. I know the Dijkstra was pretty big on proving algorithms, or he thought that was a good idea, and I did once go on a sort of, it wasn't really a date. It was, I went on a night with somebody who I think worked on a proof assistant. She wasn't very impressed by me, so maybe you could see why. Yeah, but she seemed very smart, as you would need to be, I suppose. Using this general method, the problem of proving that a given algorithm is valid evidently consists mostly of inventing the right assertions to put in the flowchart. Once this inductive leap has been made, it is pretty much routine to carry out the proofs that each assertion leading into a box logically implies each assertion leading out. In fact, it is pretty much routine to invent the assertions themselves once a few of the difficult ones have been discovered. Thus, it is very simple in our example to write out essentially what A2, A3, and A5 must be, if only A1, A4, and A6 are given. In our example, assertion A6 is the creative part of the proof. All the rest could, in principle, be supplied mechanically. Hence, no attempt has been made to give detailed formal proofs of the algorithms that follow in this book at the level of detail found in Figure 4. It suffices to state the key assertions, those assertions which are often called inductive assertions because we prove them by induction on the length of computation. either appear in the discussion following an algorithm or they are given as parenthetical remarks in the text of the algorithm itself. This approach to proving the correctness of algorithms has another aspect that is even more important. It mirrors the way we understand an algorithm. Recall that in section 1.1, the reader was cautioned not to expect to read an algorithm like part of a novel. 1 or 2 trials of the algorithm on some sample data are recommended. This was done expressly because an example run-through of the algorithm helps a person formulate the various assertions mentally. It is the contention of the author that we really understand why an algorithm is valid only when we reach the point that our minds have implicitly filled in all of the assertions, as was done in Figure 4. This point of view has important psychological consequences for the proper communication of algorithms from one person to another. It implies that the key assertions, those that cannot easily be derived by an automaton, should always be stated explicitly when an algorithm is being explained to someone else. When algorithm E is being put forward, assertion A6 should be mentioned too. Assertion A6 is this. An alert reader will have noticed a gaping hole in our last proof of algorithm E, however. We never showed that the algorithm terminates. All we have proved is that if it terminates, it gives the right answer. Notice, for example, that algorithm E still makes sense if we allow its variables mn, cd, and r to assume variables of the form u plus v root 2, where u and v are integers. The variables q, a, b, a quote, and b quote. Is that a? Should it be a quote? How's that pronounced? A tick? Are to remain integer valued. If we start the method with m equals 12 minus 6 root 2 and n equals whatever, say it will compute a greatest common divisor of such and such. Even under this extension of the assumptions, the proofs of assertions A1 through A6 remain valid. Therefore, all assertions are true throughout any execution of the procedure. But if we start out with m equals 1 and n equals root 2, the computation never terminates. See exercise 12. Hence, a proof of assertions A1 through A6 does not logically prove that the algorithm is finite. Proofs of termination are usually handled separately. So I guess he's saying we need to be able to prove that the answer is correct, or matches the right property, and also prove that the algorithm terminates. A prime. Okay, interesting. So that's the A tick, A prime. Okay. Exercise 13 shows it is possible to extend the method above in many important cases, so proof of termination is included as a byproduct. We have now twice proved the validity of algorithm E. To be strictly logical, we should also try to prove that the first algorithm in this section, algorithm 1, is valid. In fact, we have used algorithm 1 to establish the correctness of any proof by induction. If we attempt to prove that algorithm, it probably is I actually, no, probably I for induction. If we attempt to prove that algorithm I works properly, however, we are confronted with a dilemma. We can't really prove it without using induction again. The argument will be circular. In the last analysis, every property of the... Where's my scrolling going? Every property of the integers must be proved using induction. Oh my gosh. Must be proved using induction somewhere along the line, because if we get down to basic concepts, the integers are essentially defined by induction. Therefore, we may take as axiomatic the idea that any positive integer n either equals 1 or can be reached by starting with 1 and repetitively adding 1. This suffices to prove that algorithm I is valid. I would never doubt you, Knuth. For a rigorous study of fundamental concepts about the integers, see the article on mathematical induction by Leon Henkin. The idea behind mathematical induction is thus intimately related to the concept of number. Noteworthy early examples of inductive reasoning can be found in C for Massey Oshev by Levi Ben Gershon in France, and Arithmeticorum Libri Duo by Francesco Marolico, maybe, in Italy. These are from 1321 and 1557, so a fair while ago. Pierre de Fermat made further improvements in the early 17th century. He called it the method of infinite descent. The method of infinite descent. The notion also appears clearly in the later writings of Blaise Pascal. Bunch of names I'm probably going to need to learn there. The phrase mathematical induction was apparently coined by A. de Morgan in the early 19th century. See the Penny Cyclopedia from 1972, maybe? Or 1983. Oh, he's giving a list. Fine. Further discussion of mathematical induction can be found in G. Pollier's Here's a book eventually, hopefully through the process of this. Sorry, this is probably reversed. But, you know, probably at some point I will be able to make use of this as well. To hand. It's on my vanity bookshelf, the How to Solve It. What else is on my vanity bookshelf? Here's a grab bag of books. Let me flip myself so you can read these. Where am I? Here I am. It's starting to hurt my hand, but I learned to flip. There we go. How to Solve It, Black Mountain Days. On Becoming a Person by Carl Rogers. An Infinity of Lists by Umberto Eco, and Killer in the Rain by Raymond Chandler. Vanity assured. I may have read Killer. I don't think I've actually read Killer in the Rain. I should have done. I've read An Infinity of Lists, though. That's a fantastic book. Okay, that's exciting. Okay, more set theory to come. All right, where were we? Sorry, I just needed a break there. Dupolia, induction, analogy in mathematics. The formulation of algorithm proving in terms of assertions and induction is given above, is essentially due to R.W. Floyd. He pointed out that a semantic definition of each operation in a programming language can be formulated as a logical rule that tells exactly what assertions can be proved after the operation based on what assertions are true beforehand. See, assigning meanings to programs. Now that is a title. Similar ideas were voiced independently by Peter Nauer. He's a real ideas were voiced independently guy, Peter Nauer. It's not the first time he's voiced ideas independently in my research. Who called the assertions general snapshots. An important refinement, the notion of invariance, was also introduced by, is that pronounced Hoare? I think it's Hoare. He was was he the quicksort guy? Let me look him up. He's British. Yes, he is the quicksort guy. Nice. Okay, so he came up with, well, he developed this notion invariance, I suppose. He's got a great headshot on Wikipedia, I'll say that. He's really, somebody's really gone to the trouble of getting a good headshot of him for Wikipedia. Later authors found it advantageous to reverse Floyd's direction, going from an assertion that should hold after the operation to the weakest precondition that must hold before the operation is done. Such an approach makes it possible to discover new algorithms that are guaranteed to be correct. If we start from the specifications of the desired output and work backwards, see Edsger Dijkstra, A Discipline of Programming. Okay, interesting. The concept of inductive assertions actually appeared in embryonic form in 1946. at the same time as flowcharts were introduced by H. Goldstein and J. von Neumann. Their original flowcharts included assertion boxes that are in close analogy with the assertions in Figure 4. 1946. What was going on in 1946? Post-war. United States begins nuclear testing. So it's interesting because Neumann, of course, was involved in all that. So it's interesting to know where in his career that was taking place. Little fact for you, by the way, since the AI summary says in 46, the United States began nuclear testing at Bikini Atoll. So the story I have heard, which is almost too good to be believed, is that around the time that all this was going on, there was a French swimsuit manufacturer who had this notion that they were making single piece swimsuits, right? No sort of gaps, and they decided that you should, it will be very fashionable, very exciting to split the swimsuit into a top half and a bottom half. And I think maybe like the same week that they were due to announce this, a new product, the United States announced that they had been, or no, actually, I think it came out that they were nuclear testing at Bikini Atoll, which may have been post-war, I guess. And so the swimsuit manufacturers decided that they should call their new swimsuit invention the bikini, because in the same way that the Manhattan Project split the atom, they had split the swimsuit into two parts, which is why it's called the bikini. Kind of wild. Also, apparently in 1946, Donald Trump was born. So there's that too. It's kind of a long time ago. Okay, anyway. Unrelated to this, just getting distracted now. Okay. See also A.M. Turing's, wow, who isn't mentioned in this chapter? Early comments about verification in a report of a conference on high-speed automatic calculating machines in 49, and figures reprinted with commentary by F.L. Morris and C.B. Jones in Annals of the History of Computing, 6 in 84. And we've got a quote here from Turing. The understanding of the theory of a routine may be greatly aided by providing, at the time of construction, one or two statements concerning the state of the machine at well-chosen points. In the extreme form of the theoretical method, a watertight mathematical proof is provided for the assertions. In the extreme form of the experimental method, the routine is tried out on the machine with a variety of initial conditions and pronounced fit if both the assertions hold... is pronounced fit if the assertions hold in each case. Both methods have their weaknesses. Interesting. That's from 1950. The Mark I. The Mark I was a big computer, wasn't it? Yeah, let me find a photo. Let me find a good photo. That's kind of a good photo. That's probably more of a terminal, I would guess, for the 1950s. Let's see if there are any other photos. That looks more like it. And here's a definite press photo. That will load eventually. Incredible look. Okay, so that's from the manual, I guess, of this computer. Look at that. Look at that little notch in the desk. I would love that. I would love to have that in any desk that I used. And is this that could be a fridge too? Incredible. It's like a gaming PC. Fluffy. Well, Alan Turing basically talking about denotational and operational semantics back in 1950. Yeah, seems that way. Eric hey, saw your previous VOD. Do you have a schedule for these streams? I don't. I will probably settle on a schedule of like Thursday afternoons at the moment. Is probably what it's looking like, but it's not fixed. I'm just trying to get into a routine at the moment rather than fixing it, but it probably will end up being somewhat fixed at some point. Okay. So we've got some exercises. Right. Exercise 1. Explain how to modify the idea of a proof by mathematical induction. Modify the idea of a proof by mathematical induction in case we want to prove some statement Pn for all non-negative integers. That is, for n equals 0. Well, I suppose the idea here is that you might, it seems to me you start off with P negative infinity and you prove that, and then you P negative infinity plus 1, and if you can prove that, then you've got a proof for all of them, probably. But then you have to prove all the positive ones too, so it's probably not right. No, you probably start off with P0 and you prove that in some way, and then you do, I guess you must have to do this. Should we try and put that in slightly better terms than just 3 question marks? Okay. So this, I think this is the bit that's induction, and this is like a way to construct induction. A and B. Yeah, okay. So this is basically what we're trying to do up here. Well, okay, that screenshot noise was loud. Eric Haver, thank you. Okay, let me so irritating. I feel like I'm the only person who's regularly pasting extremely wide screenshots, and so none of the tooling is set up properly for that. Okay, so this is induction. I don't know what that weird. Oh no, that's just me. Ignore that. Yeah, so this is induction for positive integers, and our task is to modify this so it can also work for negative. Oh my gosh, okay. Negative integers, okay. So, and it's, if we were to try to put this in here, we would say, let's go like, it's a bit smaller. Give a proof that P0 is true, and give a proof that if all of, this is still too big. If all of P minus 1, P minus 2, Pn is all Pn minus 1 is also true. This proof, I'm guessing, should be valid for any negative, well, non-positive integer n. Oh, wait. I've messed it up. It's not, this isn't it at all. It's non-negative. Yeah. So it's not going down. I just misread the question. Non-negative. So we're saying 0 plus, sorry, terrible. Yeah, so we're saying we're starting off with P0. It's not negative integers, it's non-negative. So we're starting from 0 in this case. P0, P1 to Pn. I think this is true. I think that's right. So we're basically starting off with 0 rather than 1. Now, if that's wrong, I'll have misunderstood something probably fairly fundamental. Okay, looking at solution 1 only. Prove P0. Prove that P0 to Pn implies Pn plus 1 for all n, any non-negative, for all n greater than or equal to 0. I mean, I feel like I don't quite understand exactly what I'm saying here, but I feel like it's roughly right. Okay. That will do for that one. I'm going to come back to that one at some point in future. 2:15. So difficulty 15. There must be something wrong with the following proof. What is it? Theorem. Let A be any positive number. For all positive integers n, we have a to the power of n plus 1 equals 1. Proof. If n equals 1, a to the power of n minus 1 equals a 1 minus 1 equals a to the 0 equals 1. And by induction, assuming the theorem is true for 1, 2 to n, we have this. A to n plus 1 minus 1, a to the n, a to the n minus 1 times a to the n minus 1 over b to the n minus 1. Well, clearly something is wrong with it. We would assume that it is in the n plus 1 step, but I think it's a little beyond me. The rest, I guess, go through into other proofs, which I'm missing some prerequisites for. And they're all at a, whoa, okay, that looks wild. I'm sure that's a proof of something. Okay, so we get through to those, and we have loads of them. We've got a 50 here. $50, by the way, these numbers, in case you're not familiar, these numbers indicate things about the difficulty of the problem. And 50 is the max difficulty, which indicates it's an unsolved problem. So there are unsolved problems in these exercises as well. Okay, we've got some big maths. And then we've got, yeah. So I think, yeah, roughly I got number 1. The remainder of these, I think I need to spend more time probably building up my, I think this is not actually that difficult. I think it's probably pretty easy, but I'm at the point where my my ability to parse this is kind of missing through not having a firm enough grasp on all of the words involved. Should I give it a go? Is that just going to be frustrating? Probably. That's probably, this will actually be a good exercise. This exercise, I think, will be important because I think if I can get through this one, like that's bare minimum. That's bare minimum understanding, I think, of mathematical induction. So I think if I spend some more time with mathematical induction and I can do this one, that's like bare minimum, I think, for having the foundations. And then the rest should probably be more unlockable after that. So this will be my test problem that I'll try myself against when I come back to this section. Yeah, Wistrauss, how kind of him to put unsolved problems in the exercises. Yeah, indeed. Yeah, I think there's a funny little anecdote which he has earlier on. Which I just want to go back to because it makes me laugh. In many books, easy exercises are found mixed randomly among extremely difficult ones. A motley mixture is, however, often unfortunate because readers like to know in advance how long a problem ought to take. Otherwise, they may just skip over all the problems. A classic example of such a situation is in the book Dynamic Programming by Richard Bellman. This is an important pioneering work in which a group of problems is collected together at the end of some chapters under the heading Exercises and Research Problems, with extremely trivial questions appearing in the midst of deep, unsolved problems. It is rumoured that someone once asked Dr. Bellman how to tell the exercises apart from the research problems, and he replied, "If you can solve it, it is an exercise. Otherwise, it's a research problem." So, fortunately, Knuth has saved us from having to attempt to solve impossible problems as beginners. Wait, that was the wrong section. Okay, fine. Fine. Okay, all right. Right, how are we doing for time? Okay, we're on 2.5 hours. You know what I'm going to do? I'm going to... what am I going to do? Wow, it's again, my comment about trying to, this being performance art and producing the most boring stream possible is feeling very applicable right now. But you be the judge. Okay, so this is the induction part. Commitment. I want to understand the basics of induction to the point at least I can do question 2 here before we move further on. In order for this to happen, I will need to spend more time with it. I think this chapter is maybe, to some people, sufficient introduction to induction in order to understand it, but it is not for me. So I'm going to spend some time now with a different book. I'm going to start this one, and then I'm going to close the stream for today after I've started it, and then I'm going to resume with this other book next time. So the book we're going to look at now is... This book, by the way, is it's free online, so you can find it yourself as well. It's the Book of Proof by Richard Hammack. I think that's how you pronounce that. And I'm just going to get a feel for it first. So probably read the introduction, the preface. My goal in writing this book has been to create a very, and this hopefully should get me sort of basics proof stuff. It covers induction, but fairly late on. But I'm hoping, I'll start to feel it click at some point. My goal in writing this book has been to create a very inexpensive, high-quality textbook. The book can be downloaded from a website, blah, 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 in PDF form. Third edition, counting has been expanded. Calculus proof has been added. New examples. The core of this book is an expansion and refinement of lecture notes I've developed while teaching proofs courses over the past 18 years at Virginia Commonwealth University. So if you are interested in proofs, this seems like a decent place to start. Okay. Introduction. This is a book about how to prove theorems. Until this point in your education, mathematics has probably been presented as a primarily computational discipline. That's true. You have learned to solve equations, compute derivatives and integrals, multiply matrices, and find determinants. and you have seen how these things can answer practical questions about the real world. In this setting, your primary goal in using mathematics has been to compute answers. But there is another side of mathematics that is more theoretical than computational. Here, the primary goal is to understand mathematical structures, to prove mathematical statements, and even to invent or discover new mathematical theorems and theories. The mathematical techniques and procedures that you have learned and used up until now are founded on this theoretical side of mathematics. For example, in computing the area under a curve, you use the fundamental theorem of calculus. It is because this theorem is true that your answer is correct. However, in learning calculus, you are probably far more concerned with how that theorem could be applied than understanding why it is true. But how do we know it is true? How can we convince ourselves or others of its validity? Questions of this nature belong to the theoretical realm of mathematics. This book is an introduction to that realm. This book will initiate you into an esoteric world. You will learn and apply the methods of thought that mathematicians use to verify theorems, explore mathematical truth, and create new mathematical theories. This will prepare you for advanced mathematics courses, for you will be better able to understand proofs, write your own proofs, and think critically and inquisitively about mathematics. This book is organized into 4 parts, outlined below. I'm just going to get some comics. This whole talking for hours thing is not great for dry weather. If you ever needed to know how I apply lip balm, then that's how. Okay, that's better. Oof. All right. Fundamentals. Chapter 1, sets, 2, logic, and 3, counting. Chapters 1 and 2 lay out the language and conventions used in all advanced mathematics. Sets are fundamental because every mathematical structure, object, or entity can be described as a set. Logic is fundamental because it allows us to understand the meaning of statements, to deduce facts about mathematical structures, and to uncover further structures. All subsequent chapters build on... Let me move this further to the center. Build on these first 2 chapters. Chapter 3 is included partly because its topics are central to many branches of mathematics, but also because it is a source of many examples and exercises that occur throughout this book. Proving conditional statements. Chapters 4 through 6 are concerned with the main techniques used for proving theorems that have the conditional form. If P, then Q. Chapter 3, more on proof, proving non-conditional statements, sets, disproof, and mathematical induction. That's where we want to get to. These chapters deal with useful variations, embellishments, and consequences of the proof techniques introduced in chapters 4 through 6. Relations, functions, and cardinality. These final chapters are mainly concerned with the idea of functions, which are central to all of mathematics. Upon mastering this material, you will be ready for advanced mathematics courses such as abstract algebra, analysis, topology, combinatorics, and theory of computation. These chapters are organized in the following dependency tree. Okay. Chapters 3 and 13 may be omitted without loss of continuity, but the material in Chapter 3 is a great source of exercises. Chapter 10 on induction can also be omitted with no break in continuity. However, induction is a topic that most proof courses will include. Okay. Okay, I don't need to read that. Thank you to all of these people. Okay. Let's get into it. The chat. How are we doing? Decameron, evening. Hello, yes, hello. The only thing worse than learning calculus, having to relearn calculus. Yeah, the new book. I should change the title probably. Let me see if I can do that. Okay, that should be done. Yeah, Book of Proofs is what it's called. This is an interlude so that I can learn basically some of the prerequisites, as there are a fair amount of prerequisites for, at least for me. Oh my gosh, okay. Come on, let's go. Nope, just zoom out all the way. Fine, no, let's go. All right, good, here we go. No, that's totally wrong. Okay, no, that's so irritating. So irritating. Yep, no, that's not helpful. Sorry, 1 second. Maybe if I make the window smaller. Okay, that will have to do. This book is Creative Commons, so you can go and find this book online. Art of Computer Programming is I would strongly encourage you to buy if you want to follow along with it. Okay, where were we? All of mathematics can be described with sets. This becomes more and more apparent the deeper into mathematics you go. It will be apparent in most of your upper level courses and certainly in this course. The theory of sets is a language that is perfectly suited to describing and explaining all types of mathematical structures. A set is a collection of things. These things are called the elements of the set. We're mainly concerned with sets whose elements are mathematical entities such as numbers, points, functions, etc. A set is often expressed by listing its elements between commas, enclosed by braces. Okay, fine. For example, this collection here. Some sets have infinitely many elements. For example, consider the collection of all integers. Here the dots indicate a pattern of numbers that continues forever in both the positive and negative directions. A set is called an infinite set if it has infinitely many elements, otherwise it's called a finite set. Two sets are equal if they contain exactly the same elements. Fine. So order doesn't matter. Also, these are equal because they're in a different order, but they still contain the same elements, I think. We often let uppercase letters stand for sets. In discussing the set, this, we might declare A equal to it, and then use A to stand in for it. To express that 2 is an element of the set A, we write 2, and then this, read this as 2 is an element of A. Okay, use this element symbol, or 2 is in A, or just 2 in A. We also have these, and this is not, so not in. 5 is not an element in A. Okay, fine. Expressions like 6, 2 is in A, or 2, 4, 6 are in A, are used to indicate that several things are in a set. Okay, fine. Some sets are so significant that we reserve special symbols for them. The set of natural numbers is denoted by n. That's these. Okay, so that's the n, the special n, natural numbers n. The set of integers is z or z. Does anyone know why it's z or z? Is another fundamental set. So natural numbers is n. Natural numbers are positive whole numbers, so not including 0 or any negative numbers. And integers are including 0 and negative numbers. Okay. The symbol R stands for the set of all real numbers, a set that is undoubtedly familiar to you from calculus. Maybe not. Real numbers are, now what is that? Real numbers, the set of all possible numbers that can be represented on a continuous number line, encompassing both rational and irrational numbers. Okay, so it includes, root 2. That includes pi. That includes negative numbers, includes 0, includes fractions or decimals, point numbers. Okay, that's fine. So, but not including something else. Doesn't include imaginary numbers or infinity or complex numbers. Okay, fine. Sets need not just have just numbers as elements. The set B equals TF consists of two letters, perhaps representing the values true and false. The set C with these letters consists of the lowercase vowels in the English alphabet. The set D has elements, the four corner points of a square on the XY coordinate plane. Thus, 0, 0 is in D, 1, 0 is in D, etc. But 1, 2 is not in D. It is even possible for a set to have other sets as elements. Consider E equals these numbers, which has 3 elements. Okay, so it can have other sets as elements. So we're coming to, does the set of all sets that don't contain themselves contain itself? I guess that's related to this. Put your do a prediction on that. Does the set of all sets that don't contain themselves contain itself? I don't know how I'd resolve that one. Consider E, etc., which has 3 elements. The number 1, set 2, 3, and the set 2, 4. Thus, okay, so this has heterogeneous elements, I guess. So that's fine. Consider the set of 3 2x2 matrices. Okay, so we can have basically anything in them is what was being said here. Let us conserve as symbols denoting a set's elements. Okay. If X is a finite set, its cardinality or size is the number of elements it has. Cardinality, so that's, yeah, okay. We know about that. And it's denoted with these bars. Fine. There is a special set that although small plays a big role. The empty set is the set. This, and has no elements. We denote it as, now what is that symbol called? Okay, it can't be copy-pasted. It is called the empty set, /0. Or yeah, it doesn't have a, doesn't seem to have a agreed on name that I can see. Goal, Zal. Oh, Zal, that's the numbers. Zal, I see. Fine, great. Right. Nice. Okay, so that's earlier. We were talking about why it's that. Okay. Right. Whenever you see the symbol empty set, it stands for this empty set. Observe that the size of the empty set is 0. A cardinality of the empty set is 0. The empty set is the only set whose cardinality is 0. I guess that makes sense. Be careful in writing the empty set. Don't write a set of the empty set when you mean the empty set. These sets can't be equal because the empty set contains nothing while the set of the empty set contains one thing, namely the empty set. If this is confusing, think of a set as a box with things in it. We're back at the box. Can never escape the box analogy. Fine. Yeah, that's fine. I understand that. Basically, this is kind of, if you're a programmer, this is sort of obvious, right? Like if you, whoa, okay, that, suddenly it started raining dramatically out of nowhere. Okay. All right, let me turn that down. All right. Yeah, I don't know why it did that. Okay. At least it did in my headphones. I don't know if it did in yours. Okay. Right. This box analogy can help us think about sets. The set F equals the empty set, the set of the empty set, and the set of the set of the empty set may look strange, but it's really very simple. Think of it as a box containing three things: an empty box, a box containing an empty box, and a box containing a box containing an empty box. Thus, the size of set F is 3. The set G, which contains two elements, the natural numbers and the... testing myself here. So annoying. What is it called? I remember there's... so annoying. What are they called? Integers. Z for integers, because there's integers. That's the integers. This is integers. Is a box containing two boxes. The box of natural numbers and the box of integers. Thus, the cardinality of G is 2. A special notation called the set builder notation is used to describe sets that are too big or complex to list between braces. Consider the infinite set of even integers E, which is continued, I guess. In set builder notation, this set is written as 2n for every n in these integers. Okay, so it's like a function, kind of. It's kind of neat. We read the first brace as the set of all things of form, and the colon as such that. So the expression E equals 2n, well, E equals the set of all things of form 2n such that n is an element of the integers. The idea is that E consists of all possible values of 2n where n takes on the values in the set of integers. In general, a set of X written with set builder notation has the syntax X, expression and rule, where the elements of X are understood to be all values of expression that are specified by rule. For example, above E is the set of all values of the expression 2n that satisfy the rule. Is that a rule? Okay, so the rule is this. We're calling this a rule, which is sort of funny. N is in. Okay, so this is a rule because it's kind of an assertion almost. We're saying n is in is an element of the integers. I would have naturally assumed that this is like an enumeration, but they're calling it a rule, which is fine, and that'll probably be important to shift my perspective on. Okay, rule n is in the set of integers. There can be many ways to express the same set. For example, E equals a set of elements such that what is it? E equals the set of all things of form. E equals the set of all things of form 2n such that n is an element of the integers. Let me get that in my head. E equals the set of all things of form 2n such that n is in the set of integers. N is an element of the integer set. Okay, one more time. E is a set of the form. No, E equals the set of all things of form. E equals the set of all things of form 2n such that n is an element of the integers. Okay. Get that in my brain. Okay, and then we've got this other form here, n, where n is an even integer, n, where... So this is okay, right, that's what this is saying. I skimmed over this. Expression, rule. So there's different ways to put this rule and different ways to put this expression. Okay, so the rule is, so the expression is n, and the rule is n equals 2k, and k is an element in the set of the integers. In the integer set, or something. In integers, probably is the right way to say. Another common way of writing it is n is an element of the integers such that n is even. So the colon is like a such that, I think, such that. Read E is the set of all n in the integers such that n is even. Some writers use a bar instead of a colon. For example, E is a set of all the elements n that are elements of the integers such that n is even. We use the colon. Fine. So there's a bar syntax as well. But this book's going to use the colon. Okay. Here are some further illustrations of set builder notation. Okay, n such that n is a prime number. N in the elements of, is there a way to put this? E is the set of all n in Z. Okay, the set of all n in the real numbers? No, wait. Natural numbers for n. Natural for n, Z for integers. The set of all n in the natural numbers such that n is prime. Set of all n squared such that n is in the integers, such that n is an element of the integers. Set of, come on brain, set of all x in the, I assume, real numbers such that x squared minus 2 is 0. That's just two elements. 5 is the set of all x in the integers such that x squared minus 2 is 0. That's the empty set, because there's nothing, I guess, that satisfies that. Set of all x in the integers such that the absolute value of x is less than 4. Set of all 2x such that x is in the integer, such that x is an integer and the absolute value of x is less than 4, sorry. Fine. And the set of all x in the integers such that the absolute value of 2x is less than 4. Okay, fine. Okay, whoa. Items 6 to 8 above highlight a conflict of notation in that we must always be alert to. The expression bar x means absolute value if x is a number and cardinality if x is a set. The distinction should always be clear from context. Consider x is in the set of the integers where the absolute value is less than 4. In example 1.1.6 above, here x is in the integers, so x is a number, not a set, and thus the bars in bar x must mean absolute value, not cardinality. On the other hand, suppose A was a set of sets like this, and B equals B is the set of x in the set. All the elements x in the set A, where the cardinality is less than 3. The elements of A are sets, not numbers, so the bar x in the expression for B must mean cardinality. Therefore, B equals this result. Okay. Example 1.2. Describe the set. A is the set of elements 7a plus 3b such that A and B are in the set of integers. So I guess we're talking about Yeah, we're talking about these two values. This set contains all numbers of form 7a plus 3b, where a and b are integers. Each such number 7a plus 3b is an integer, so a contains only integers. But which integers? If n is any integer, then... Wait, what is going on here? This set contains all numbers of the form... Okay, of the form is probably an important word. Of the form 7a plus 3b, where a and b are integers, each such number 7a plus 3b is an integer, so a contains only integers, but which integers? If n is any integer, then n equals 7n plus 3 multiplied by 2n Where's this minus 2 coming from? I don't know. N is 7a plus 3b, where a equals n and b equals 2n. Where's the n coming from? Okay, where a equals n and b equals minus 2n. Therefore, n is in the set of a. We've now shown that a contains only integers and also that every integer is an element of a. Consequently, a equals the integers. Okay. Well, there's something going on there that's not quite clicking for me now. We close this section with a summary of special sets. These are sets that are so common they are given special names and symbols. The empty set, the natural numbers, the integers, the rational numbers, that's this Q, I guess, keep in mind the Q, and the real numbers. We visualize the set R of real numbers as an infinitely long number line. Wait, so rational numbers are x such that x can be represented as m over n, where m and n are in the integers and n is not 0. So these are numbers that can be represented as fractions. I guess that's what rational number means. Okay. Notice that Q is the set of all numbers in the real numbers that can be expressed as a fraction of two integers. You may be aware that Q is not equal to R, as root 2 is not in Q, cannot be represented by a fraction, but root 2 is in the real numbers. Yeah, okay. Well, we will discuss this later potentially. In calculus, you encountered intervals on the number line, like real numbers. These two are infinite sets of numbers. Any two numbers a and b in the real numbers with a is less than b give rise to various intervals. Graphically, they're represented by a darkened segment on the number line between a and b. A solid circle at an endpoint indicates that number is included in the interval. A hollow circle indicates a point that is not included in the interval. Okay. Right, so we've got different kinds of interval here. Closed intervals, open intervals, half-open intervals. Two kinds of half-open. Okay, we've got some notation here. So we've got closed intervals, which are like this. Open intervals, which are... So these are in what I would call inclusive. These are open intervals, so they are exclusive. Half-open intervals, which are inclusive at the top end, which is a square bracket at the end. I guess the square bracket means inclusive, kind of. Half-open intervals that are open, that are. What does the open mean? I guess this must be closed. So closed. Okay, wait. Oh my gosh. Let me get this in my brain. Okay, so closed kind of means inclusive. Open kind of means exclusive. in my intuitive understanding. Half open at the top would have a square bracket at the end and includes the top value. Half open at the bottom has a square bracket at the bottom, has the first value and is inclusive over the first one but not the second one. An infinite interval just has a starting point and it's goes on forever. An infinite interval that is closed at the bottom, closed meaning inclusive. I'm going to get those words mixed up so much. Closed, okay, let me get it in my head. Closed means inclusive. Okay, how can I get that in my brain? Closed, inclusive. If, okay, what will help me remember this? Does anyone have any mnemonics? Square bracket number is included. Yeah. The term closed. Okay, so if I want to include someone, let's say I want to include someone, I'm gonna close my arm around them in a nice way. I'm gonna close my arm around them as like a sort of hug. So I'm gonna close my arm around them because I'm including them. If it's an open interval, I'm going to open my hand and push them away. And I'm just going to have to remember that closed interval is square brackets and open interval is round. I guess I can say closed interval looks a bit like a door. Open interval looks like a kind of, you know, kind of looks like a circle. Yeah, okay, that's interesting. Wait, Wistras. Yeah, infinity is always open at its end, so yeah, it's always going to have this round edge. You're never going to have a square bracket on the end. Okay, and we've got negative intervals too. Fine. Negative infinities too. Okay, each of these intervals is an infinite set containing infinitely many numbers as elements. For example, though its length is short, the interval 0.1 to 0.2, which is it's an open interval because we got these round brackets, and this is going to be a less than and a less than and a greater than. That's what my memory is telling me right now. A less than or greater than, not a less than or equal to. So that's correct. Great. Okay. Important to do the retrieval practice. One of the techniques, by the way, I always used to give to my students was because closed, you draw a hard boundary there and that boundary point is included. Open, you have this soft idea of a boundary there, so you can get closer and closer to it but never quite touch it. Thank you, Lorsayer. Yeah. I get the idea. I just know I'm going to forget the vocabulary at some point. Anyway, so technique I would always give my learners when they were learning to code is try to just remember things as much as possible. Like your brain, if your brain's going to put things in its memory, it needs to be encouraged by you proving to it that you're not just going to look things up, that it doesn't have that information available. If you always have something available, you'll notice your brain just doesn't seem to remember, like in my mind, the brain doesn't want to remember things it has reference to easily because it's a waste. However, if you force yourself to try to recall it, even if it's right in front of you, then you're going to be just pushing more information into your brain. So this is a open interval. It's going to be with less thans and greater thans, not less than or equal tos. Contains infinitely many numbers, makes sense. That is all numbers between 0.1 and 0.2. It is an unfortunate notational accident that AB can notate both an open interval on the line and a point on the plane. I guess that's true. The difference is usually clear from context. In the next section, you will see yet another meaning of A, comma B. Oh my gosh, okay. Got a lot of exercises to do here. 52 exercises. How much energy does my brain have left? Probably some. All right, time to do my homework. Okay, let's go. Let's get the homework. Get my homework brain on. Okay, all right. Window management. Let me put this over to the side. Let me put this here. Okay. I think I should be able to see everyone now. Good. All right. Okay. Let's go. Let's get this done. 1.1 A. Okay, write each of the following sets by listing their elements between braces. Okay, so we're in the... Let me try and zoom this in a bit. Okay, cool. All right, so we're in the integers, and we want to get everything that's 5x minus 1. Isn't that going to be... Isn't that going to be infinite? Is that going to be an infinitely long? I guess we can probably just list some of them. I guess, yeah, I guess it's asking us to list them a bit like this. I guess that's probably what it's asking us to do. Unless, I mean, I guess it never terminates if we write it. Okay. So actually, no, it's integers. It's integers, and they can be negative. So it's going to be ... comma, and let's go with like the, I don't know, the minus 2. The camera says, I would love your contagious enthusiasm of doing homework rub off on my kid too. Yeah, I mean, it's one of those things, right? Youth is wasted on the young. You'd always so much more enthusiasm for learning as an adult. And yeah, for children, it's harder, I guess. Okay, anyway. Minus, so this would be, let's say, let's go with minus 2. Minus 2 times 5. My phone is almost out of battery. Okay, that's fine. Interesting. Okay, minus 2 multiplied by 5. Minus 1 is 11. Sorry, minus 11. Minus 11. Then that would be minus 1 times 5 minus 1 is minus 6. Okay, fine. Then if we have 0, this is going to be minus 1. Then we're going to have 5 times 1 minus 1, which will be 4. 5 times 2 minus 1 is going to be 9. Then we have these dots here. I think that's right. Okay. It's going to be it's in the integers again. So we'll have minus 2, that's minus, so that's minus 6 plus 2 is going to be 4, because it's 3 times minus 2, that's minus 6, plus 2 is 4. 3 times minus 1 is minus 3, plus 2 is minus 1. Then for 0, we've got 2. For 1, we've got 3 plus 2 is 5. Then for 2, we've got 6 plus 2 is 8. I got those. Then we have, for the elements in the integers again, where they are, so between starting at -2, -1, in fact, I don't even need that, -2, -1, 0, 1, 2, 3, 4, 5, 6, but not 7. Hello, Matrixcraft. Okay, 4, we've got for x in the natural numbers. Now, natural numbers are not including 0 or any negative numbers. So we're going to start with 1, 2, 3, 4, 5, 6, and 7. Long time no see. How's it going? It's going well. Yeah, we're working through the art of computer programming. This is not the art of computer programming. This is some brain tired. Preparatory materials. This is a book of proof. So I'm trying to learn some proof stuff before I go back to the mathematical induction section in the art of computer programming and ace it. So that's what we're doing now. We're doing our homework. Okay. So 5. X, yeah, so x is an element of the real numbers such that x squared is 3. Well, it's going to be root 3. What is root 3? 1.7. So let's say, well, do we do like, because I mean, this is 2 numbers, right? Sorry, I sounded so horrified. It's 2 numbers, right? The square root of 3. So this isn't kind of... Do we have 2 elements here? Do we want to put 2 elements here? I don't know how we notate that. Probably not in Excalibur. Let's put in like minus 1.73. And then that. I think that intuitively that seems right. I don't know. We'll look at the answers and see at some point. Okay. X in the real numbers where x squared is 9. That's going to be minus 3 and 3. X in the real numbers and x squared plus 5x is minus 6. Now, what are those elements actually? X squared. Let's go with like 1. 1 plus 5x. I have to do some maths here. Do some proper maths. Yeah, I can do that by trial and error. There's probably a way to solve that. There's probably, do you factorize it? Yeah, I think I remember doing this at some point. There was like a, something like this. But yeah, I don't remember the actual way you do that. Wow, I'm not even up on my algebra. I'm going to have to revise my algebra. Terrible. Really terrible. Okay. Let's try it by... It's also possible there's no actual solution to this. It could be in the empty set. Okay, so let's try this with minus... So, okay, what is it? What is it again? Let me put this again. Can you get it into the x squared plus bx? I guess so. Yeah, okay. So, yeah, okay. So, yeah, that's a good hint. Thank you, law sayer. Okay, so in that case, if we have this, then we can subtract, no, we can add 6 to both sides. And then there's another step after this. I guess there's like a quadratic formula for this, right? If you or something. I really don't want to break out the quadratic formula, but I could. Oh, I see. And then we put it into that form. I see. Okay. And then I think at school I learned this purely by guesswork. I don't think we had any routine for it. Okay. So right, and then Nagweed, hi. I'm doing well, thank you. How are you doing? Okay, so now for this to work, these numbers multiplied together have to be 6. And that leaves us only a few options. 1 and 6. Well, I guess it's in the real numbers, so there could be an infinite number of options. 1 and 6, and then if we multiply, and these have to add to 6, so we have to have like well, there could be negatives, but that would be unlikely. 2 and 3. Oh, I guess it'd be 2 and 3. Could be 2 and 3. Yeah. And then this gets us a solution, right? We use the trick back in school. List the factors of +6, then check for the sum of the factors. Yeah. I guess that's what I was doing in my brain there without noticing it. Yeah, and then there's a way that you get to the solutions from this. And I think it's based on these numbers. Let me look this up. Yeah. So we rewrite that. We set each factor to 0. Ah, yeah, okay, wait. It's coming back now. I say it's coming back. The AI summary is bringing it back for me. Okay. So in this case, this is going to be this resolves this. Another way of describing this is this, because one of these will have to be 0. One of these factors, one of these brackets will have to be 0 for this to end up being 0. So we end up with this, which is, we can get rid of the brackets on and say this. Which means we're going to get x is -2 and x is -3, I think. We can double check this by putting it back in. X squared plus 5x. So if -2 squared is going to be, no, thank you, calculator. That's not right. So minus 2 squared, sorry, minus 2 squared is 4 plus 5 times minus 2 is minus 6. Okay, great. And then the same with minus 3. That's the same. Okay. Thank you for the help, everyone. Minus 2 and minus 3. Everyone, I say Lawsayer and Nagri, thank you for the help. Okay, so those are the two solutions. So I guess those must be the elements of the set. We would think. Okay, and then we get to an even more fun version. Now this looks, it looks like I can apply the same, I don't think I've applied this with cubes before. But in theory, it should still work, right? If we want to do this, in fact, it's exactly the same, right? We don't even, it's exactly the same. But is there going to be some minuses in there? Is there going to be some minus stuff? Well, let's try out those two solutions and then we'll find out. So minus 2 cubed plus 5 times minus 2 squared equals 12. 12. 12 is an important number. Remember 12. And then minus 6 times minus 2 is 12 as well. So that solution also works. And so if we plug in minus 3, we get 18, and that's, yeah, that's clearly true. Okay. So I think these sets are the same. Or is it... yeah, I think those are the same. I think they're the same. Okay. All right. Let's keep going. My phone, which is... I'm forgetting one more. Huh. Okay. I'm forgetting one more. Tempted to just try it. Okay. 0 cubed is going to be 0, plus 0 is minus 6, 0. So 0. And we should probably put them in order. And 1 is not valid there. Yeah, okay. So I think it's 0. 0 plus 0 is 0. Minus 0. As long as minus 0 and 0 are the same, which they are. Hans Bemble. I'm also too dumb for this, but we must persist anyway. Or I must persist anyway, because the stream will be extremely frustrating otherwise. Okay. Right, let's get through these 9 through 16. My webcam is running out of battery, so that will put a natural conclusion to things. After that, okay, x is in the real numbers such that the sine of pi multiplied by x is 0. Okay. Sine pi What is the sine of pi? 0. The sine of pi is 0. And so the sine of pi times x, I assume that we're talking about, I don't get the order of operations here. X is any whole number, yeah. That's the way it's seeming. Yeah, so the order of those operations is, or the sign is sticky to, no, the pi and the x are sticky. So we execute pi and then x first, and then we compute the sign of them. So any multiple of pi should be 0. I think that's true with sine. Or is that not true? No, any multiple of pi is 0 signed. So yeah, any whole number is right. Negative numbers. The sign of negative pi is also 0. Okay, so it's like basically it's this basically. So it's z. It's the big z. It's the integers, I think. Okay, and then where the real numbers where the cosine of x is 1. So the cosine of x is 1. Let me look at, I assume we're talking about radians here. Let me look up a, let me copy this in so you can see it as well, see what I'm looking at. So we're interested in the case where the cosine of x is 1. That's at 0 and 2 pi. And since it's cyclical, it'll be something like 0, 2 pi, 4 pi. I don't think it matters that it's negative, so we can have negative 2 pi. So another way we could put this is x in z, where such that 2n x times pi in this. So I think this would then, is that such that 2n is, no wait. Is this right? Okay, 2 times, so for all of the integers, positive and negative and 0, we're looking at 2n multiplied by pi. I need to get the pi symbol in my keyboard shortcuts. I think that's right. 2 pi, 4 pi, 0 pi, minus 2 pi, minus 4 pi. I think that's right. For all of these instances, cosine x will be 1, I think. So let's take a random n just to check this out. Let's say n is this, and then if we were to use times pi cos times 2 times pi, we get 1. Let me put in some other numbers. We're always getting 1. If I put in 0, I need something better I can share with you on this. I know you can't see it. Okay, all right, need a better calculator. All right, so that seems to be right. X in the integers where bar x is under 5. So we're looking at the absolute value of x. So we're looking at -4, -3, -2, -1, 0, 1, 2, 3, 4. I think that's right. Now we're looking at the same thing, but for 2x is less than 5. So we can filter this down. I think we're looking at -2, -1, 0, 1, and 2. Okay, 6x is less than 5, so that's just 0, I think. Okay, 14. 5x such that x is in the integers and the absolute value of 2x is less than or equal to 8. Let's start off at 0. 0 goes because I think there's a funny bit of noise happening on the audio track. And there's some sort of animal screeching. Okay. Anyway, got to get this finished. All right. 5, 0. Yeah, fine. Okay, now 1 times 5. So that let's try 5. That would be 1. X would be 1. X is in the integers, and 2x, that's 2, is less than or equal to 8. Fine. Okay, 10, that would be 2. 2 times 4, no, 2 times 2 is 4. You heard it here first. 4 is less than or equal to 8, so we're fine with that. 15, x would be 3. 3 by 2 is 6, and that's in the condition. 20, that would be 4. 4 times 2 is 8, and 8 is less than or equal to 8. But for 25, it would be 5, and in that case, we've got 10, which is not valid. This also should be applied to the negative versions of each of these, I think. In fact, for the negative versions, no, because we've got the absolute value. I think that's right. We've got that. $15, okay. 5a plus 2b, where a and b are in the integers. So let's say we start off at 0. That would be 0. This would be 5 plus 2, so we'd have 7. If we had no, wait. These can be different. So we'd have a big old range. We'd have a big old set of these, now I think of it. So if they're both 0, let's keep track of this. Let's say they're both 0. If they're both 0, then we have 0 in the set. If they're both, if we have 1 and 0, then we've got 5. If we've got 1 and 1, then we've got, sorry, that's not right, 0 and 1. If we've got 0 and 1, we've got 2. Am I just going to list all these out? Surely not. In this case, we've got 7. If we order these, we get 0, 2, 5, and 7. Is there a pattern we can rely on? That's 10 plus... No, there's not going to be no pattern we can rely on. Or will there? Well, okay, so let's consider the situation in which A is 0 always. In that case, we're going to get... we're going to get 0. Well, ignoring the negative numbers for now. We're going to get 0, we're going to get 2, 4, 8, 6, 8, etc. So that we're going to have one set there. And we're going to have to add to this, for example, we're going to have to add to this where B is 0, where we get 0, 5, 10, 15, and 20, etc. And so it's all of the... Any number which is a multiple of 2 and 5 will automatically be in there. Can we get numbers which are not multiples of 2 or 5 in there? We could get, for example, 7. Could we get 7? I think we had something like 7 earlier. Let's say we had 1, 5 plus 1, 2 is 7. Oh yeah, obviously we can. So we could get 7 in there. So there's going to be some way of adding these together. We're going to get all multiples of Can we make all the numbers out of this? Probably, yeah. Probably. Let's see if we can make 1. If we can make 1, probably we can make all the rest. In that case, we could have A being 5 and B being -2, which would be 5 minus plus minus 4, which would give us 1. So I think we can make all the integers with this. I think if we can make 2, can we make 3? Yeah, we can make 3 because we can have a -2 and a 5 positive. So we can make 3. We can make 4. We can make 5, obviously. If we can make all them up to 10, then we should be able to probably not prove this, but it seems that way. We can make can we make 6? We can make 6 out of 2s. We can make 7s, we know that. We can make 8s by giving 10. No, wait. How can we make 8s? How can we can make 8s by having 10 minus 2. We can make 9s by having 5 plus 4. And we can make 10s. I think it's all the integers, but that is a bit of a guess. And I think it can be all the negative and positive integers. So I think it's just that. Now this one, however, cannot be all the integers. This 16th. Well, it's getting rainy, huh? Let me turn that down. Yeah, so I think that's all. I think that's all the integers. Now 16 is different because we can only ever get even numbers. But I think we can get them all. We can get 0 for sure. We can get 2. We can get 4. We can get 6. Yeah, I think we can just get all the even numbers. So I think we can say that this is 2n. I think that's probably right. Okay. Let's see. Let's look at the answers for these. And then that'll be the close of the string. If indeed there are answers, may not be. 292. Okay, we're almost there. Most exciting part of the stream. 292. Okay. It's not given us all the answers because it's a maths textbook, I guess. 1. Okay. Yeah, 11, 6, yeah, 9, yeah. Okay, we were supposed to do that. Great. Minus 2. Okay, that's wrong. No, wait, that's 3. That's 3. 3. Okay, 3. Minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6. Great. 5. Okay, he's only giving the odd ones. That's fine. 5 is okay. Yeah, great. So I was the preferred notation, I guess, is this. I didn't put this down because if this is like, if we were to consider this a set of 2 numbers, it's like indeterminate. So I wasn't really sure. But I guess this is the way we notate this. 7 minus 3 and minus 2. 9 is minus 2, minus 1, 0, 1, 2, 3. I guess, yeah. Yeah, fine. Okay. 11 minus 4, minus 3, minus 2, minus 1. Yeah, fine, great. 13 empty is a set of 0 only, not the empty set. 15 is, yeah, the integers, and 17 we haven't got to yet. Okay, so, well, at least all of the ones that I have the solutions for are correct. With thanks to chat for a little extra tutoring. Okay. All right, that is enough. There's enough study for today. I can get one for 15, not 16. Yeah. Thank you, Lorsayer. Thank you. All right. Wow, that was a real journey. That was a real journey. Okay. How exciting. Well, anyone else doing anything exciting today? With my last few moments of webcam battery juice, anyone want to tell me anything exciting they're doing? Unless maybe they're just doing this. Maybe they're just studying. Thank you for all the follows, by the way. At some point I may or may not put various flair on the screen. such as I see other streamers do. Actually curious to know if anyone thinks that's a bad idea. I veer against it because I kind of it's not that I'm not appreciative. I more think maybe if you're watching this type of stream or you're watching the VODs, then you want to be able to focus a bit better. And some people I know find it hard to focus with those kinds of noises and such. So I've left that off. But yeah. Anyway, that was exciting. That was very exciting. It was like 2 hours of like impossibly hard computer science math, and then maybe an hour and a half of somewhat more manageable textbook math, which I could basically do. But it was a little challenging, which I guess is the point. Spicy Corsair, I want to do some studying and get to visit the dentist this afternoon. Ah, wow, that's exciting. Are you having anything exciting done at the dentist? don't need to tell me. You don't need to tell me. But if you are having anything exciting done at the dentist, I hope you are. I have a fantastic dentist. Very unusual for the UK to have a good dentist, but my dentist is very good, or at least I say he's very good. He convinces me he's very good by telling me how good a toothbrusher I am, which of course I like to be recognized. So I guess maybe he's a terrible dentist, but he seems like he would be good because of that. All right, who else is streaming at the moment? Let's see what's up. See what's going on in the software and game development world. And I want to, yeah, okay. Who's around? Who's doing anything interesting? A lot of game dev, classic game dev day. Somebody's studying Android system design. That sounds interesting. Somebody's having fun with RISC v64. Okay. Let's see if we can find anyone interesting to tune into. It's not really my time of day. I suppose I'll get used to who streams at this time of day. Android system design sounds sufficiently dry. Maybe we'll find out. Let's see whether this person is streaming in English or not. Indeed. All right. Let us do some rating. We're going to find out what Android system design is happening in Frozea's channel. Thanks for tuning in today. Hope you have a good rest of your day, and I will probably see you next week. Almost certainly see you next week for another edition of trying to do all of the art of computer programming, probably with a bit more focus on maths still, while we try to get to induction. All right, thank you, and goodbye. The requisite delay of 7 or so seconds. Let's do it.